back. Last time we learned how to implement Euler's method on the computer using Wolfram language on Mathematica, and we learned how to solve problems using Euler's method, how to solve ordinary differential equations in one dimension using Euler's method. Today we are going to learn how the error propagates in Euler's method, that is how the step size matters in the precision of the calculation, and we'll also see how to solve more multi-dimensional problems, that is two-dimensional problems or three-dimensional problems using Euler's method. And this will be our steps to build on to more rigorous, more complicated methods such as Runge-Kutta second order, Runge-Kutta fourth order. So let's go ahead and get started. Just a quick review of Euler's method. We have a differential equation x dot equal to f of xt and some initial condition x of t naught equal to x naught, and this is how we implemented it. We wrote down a for loop. We used module construct to construct a single function which has a bunch of inputs. One of the arguments or input of the function Euler that we defined was function, initial value of x, initial value of time, final value of time up to which we want to evolve or we want to solve the differential equation, and number of steps, which is n max. First we calculate h as tf minus ti over n max. Then we start our for loop, and in each step we calculate the next step for x. This is the initialization step. We define the first element of data list, which is the solution that we are looking for. So our solution is stored in the data list. The condition is length of data list should be less than n max. We decided to, then in the increment part we are appending data list with the previous plus the increment, and this increment is both the increment in time and increment in x. F acting on the previous value is giving me the derivative, which multiplied with h gives me delta x. So h is the increment in time, h times f of x and t is increment in x, and together is added to the previous, which is a two tuple, and in the body we are just simply reading the, or we are updating the previous, reading the last element of data list. So in that process for loop generates the entire solution, and at the end of the for loop we return data list that ends the function. So I'll go ahead and execute it, and that's my Euler function. Since Euler function we are evaluating with this with h size h, that is we are solving a differential equation x dot equal to f of x, and in that process in the Euler's method we are calculating delta x n plus 1 as f evaluated xn times h or delta t. So this is accurate up to h, which means that xn f delta x is accurate, or this is accurate to order h square, because this is already order h. So delta xn is correct up to order h square. So this is correct up to order h, and the correction is order h square. So I know delta xn with accuracy of h square. Therefore local error is of the order of h square. But that means the correction in xn plus 1 corresponding to xn, oh sorry, I'm missing xn over here, I should have a summation over xn. A determination of delta xn plus 1 in comparison to xn is accurate to order h square. The correction itself is of order h, and the error in it is going to be at most order h square. Now, so at each step we are making a correction of order h square, but we have to do of the order of n max steps. So by the time we reach to the end of the solution, the number of steps involved is of the order of n max. So therefore n max times order h square is n max times h, and n max times h is nothing but tf minus ti, which is an order 1 number, and this is h. So therefore global error, this is the global error, global error becomes order h. And this is exactly what we are going to analyze now using numerics. So let's go back to our code. In order to find out the global error, what we are going to do is we are going to calculate the error using this formula, where we are going to take xi, which is the xi that we computed, and f of ti, where f of ti is the analytical solution at time ti. So ti is the expected analytical solution and xi is something that we have computed. We take the difference of the two, take the absolute value and sum over all i's from I equal to 1 to n, and then we divide by n to calculate the mean absolute error or mean absolute deviation. So in order to do that, we'll again use the module construct, and we wrote down the error function. This is something we did last time, so this is a quick review of that. We wrote down the error function. This is the error function. In the error function, we again use the module construct. T list, x list and fx list were the three lists. T list, we extracted the first element of the data set. Data set is the argument that we are passing. This data set is the solution that we obtained through Euler method. That is this data list that the Euler method returned. We are passing that to the error function. This error function, the first element is the time component and second element is the x component. This stands for all the rows. So we extracted the time component, we extracted the x component, then we calculated a list of true values of f by applying the function, that is this function, which is the big F, the solution of the differential equation. We applied f at t list to obtain the true values. Then in order to find the mean absolute error, we took the difference of x list and t list, applied the absolute function on it through postfix application, and then calculate the mean again through postfix application, and then return that to give me the mean absolute error. So let's say the function that we are trying, the function for which the solution that we are looking for is, let's go ahead and do what we have been doing so far. Let's start out with minus 2x. So let's say our differential equation, that is x dot equal to f of x. So this is little f of x t, which is what I've defined over here as minus 2x. This ff is the function that I'm going to pass to the error function. This is the solution of the differential equation, and in this case, if x dot is minus 2x, then the solution is e to the power minus 2t. So let's go ahead and do that first. And so this is my derivative x dot, this is the solution, x is a function of t, and here is the table that I've constructed. The two elements of this table, this is tf minus ti. I'm taking tf as 5 and ti as 0, so tf minus ti is 5 divided by 10 to the power n, which is n max. To the error function, I'm passing two arguments, the Euler and the solution f. This is the Euler list. Euler function is going to return me data list, which is the solution for x dot equal to this f from x ti equal to 0 to ti equal to 5, for x0 equal to 1 and n max equal to 10 to the power n. So this is going to return, the first argument is going to return me data list. That data list is passed to error function, and then error function is also passed the solution and is going to find the difference in the mean absolute error. I'm dividing that mean absolute error that I'm obtaining from the numerator over here by h. Let me for now let me go ahead and remove that. So we're going to just take the error, mean absolute error, and we're going to execute it for n equal to 1 to 4. So we're going to get 4 values, n equal to 1 to 4, so 10, so n will be 10, that means n max is 10, and then n, when n is 4, n max is 10,000. So for 10 steps, 100 steps, 1000 steps and 10,000 steps, we're going to execute this. So this is going to give me, oh, I think I forgot to define the error function. Let me go ahead and define that. Okay, now I'll execute it again, and this is going to give me the value of h. So each of these pairs is giving me a value of h that I'm using over here and the corresponding error. And as we see that as h decreases, proportionately error also decreases, the mean absolute error also decreases. So this is the global error that we're looking at. If I divide this global error by the value of h, which is this. Let me copy that and paste it over here. And when I execute that, you see we're going to get approximately a constant. So for h equal to 0.5, we are getting mean absolute error by h as 0.1. For 0.05 also mean absolute error by h as 0.1, and so on. Even for h equal to 0.0005, I'm getting the same thing. You can go ahead and change. For example, I can change tf to 10. If I change tf to 10, this is ti minus tf. So this also I should change to 10, and this also I should change to 10. And I can execute this again, and you see that the first one, the error was, the h was too large. H was 1 because 10 over 10 is 1. So that's something that is an outlier. So we leave this one out. But apart from that, for small values of h, when h is 0.1, 0.01 or 0.001, we see that mean absolute error divided by h is a constant. This is a numerical check of the fact that we laid out, that global error in Euler method scale like order h. And that's what we are seeing over here. We can go ahead and try out something else. Let's go ahead and try out x dot equal to minus xt. The solution of that is a Gaussian, so the solution is e to the power minus t square over 2. You can go ahead and check that out, and we are going to go ahead and execute this again, and we see that again, that pretty much for all values of h that we have taken over here, mean absolute error divided by h is a constant. Therefore, the error is of the order of h, or the error scales like, the global error scales like h. Alright, so you are welcome to go ahead and play with this a little bit more for various different functions that you can try out for various different x dots that you can solve and find the analytical solution. Feed that in, run this a few times to find out how, in your examples that you take, how does the mean absolute error scale. Alright, let's go ahead and work on how to reduce higher order ODEs to first order ODEs, because what we have learned in the Euler's method is that if you give me a first order ODE, I can use Euler's method to solve that first order ODE. However, most of the time in physics we don't come across first order ODEs, we come across second order ordinary differential equations. And if we want to use Euler's method to solve second order ODEs, then we need to reduce those second order ODEs to first order ODEs so that we can apply the Euler's method. So in order to understand that, let's go back and go to the familiar example of LCR circuit and obtain a second order ODE. If you go back and review the LCR circuit example, this is the differential equation we obtained: d square q by dt square equal to minus q by LC minus I by L dq by dt. For this differential equation, the initial conditions were q0 was q0 and q dot 0 was 0. Now in order to apply Euler's method, this is second order differential equation, we are going to reduce it to first order differential equation by defining an auxiliary quantity. In this case, we'll call that I equal to dq by dt, which is also physically meaningful. I is the current, I equal to dq by dt. So we'll use I for dq by dt, and we'll use d square, we'll replace d square q by dt square with di by dt. So therefore now we've got two equations, I equal to dq by dt and di by dt equal to minus q by LC minus R by Li. So this set of two equations is equivalent to this second order equation. Now the interesting thing is that this set of equations, these two equations, they're both first order in derivatives. This equation is first order in time, it has only dq by dt. This equation again is first order in time because it's got di by dt. I itself is dq by dt, but we are not considering I as dq by dt. We are taking I as a independent variable, q as independent variable, and we have got two coupled ordinary differential equations of first order. And the initial conditions also modify accordingly. q0 becomes q0 and I0 becomes 0. Rather than writing q dot equal to 0, q dot is I, so we say I at t equal to 0 is 0. So we modify both the initial conditions and the set of differential equations reducing them down to first order ODEs. Now I can go ahead and use Euler's method, because I know that in order to solve this equation with Euler's method, I can calculate dq's in steps by finding out I times dt, previous I times dt, and in order to find I, all I have to do is use this equation which says di by dt is this right hand side. So I calculate this right hand side at previous time and multiply by dt, and that will give me di. So I can calculate subsequently dq steps and di steps and keep on incrementing them, and by doing so I can implement the Euler's method to find out both I as a function of time and q as a function of time. Now that you have got the gist of it, you can go ahead and generalize it, and here is how the generalization works. Let us consider a general nth order ODE. For example, nth order ODE dxn by dtn is a function of f and is given by f, which is a function of time x, x dot, x double dot, and so on. X to the power n minus 1 means that n minus 1 is derivative of x with respect to time. So in general, my nth derivative can be written as a function of all the lower derivatives and the time. Therefore, most generally I am to deal with such a differential equation when I am talking about ordinary differential equation, and such an equation I can reduce to a set of ODEs by using the following trick. For every quantity such as x dot, starting with x dot, I will define x dot as y, and then I can take x double dot as d by dt of x dot, which is y, so y dot becomes z, and then so on. I can write s dot equal to w, where w is the, or rather w is s dot, should be other way around, w is equal to s dot, where w is the n minus 1th derivative of s, and then my w dot, which is the nth derivative of x, becomes a function of t, x, y, z, s, w, etc., which is where I take t, x, y, z up to w, all of them as independent variables, and I simultaneously evolve them using this set of differential equations, where this is the equation of motion that was given to you, and these are the auxiliary equations that you wrote down in order to convert this equation into a set of first order ODEs. Now notice that all of these equations are first order differential equations. So now if we can go ahead and implement Euler's method on that. So let's go ahead and prepare this LCR circuit for numerical evaluation. There's one more step that we need to do before we can actually employ Euler's method. So remember the 4 steps of our computational thinking approach: define, translate, compute, and interpret. What we are going to do now is we'll work on the first 2 steps, define and translate. Then compute and interpret is something we'll do on the computer using the Euler's method, and define and translate we need to do on pen and paper in order to translate our LCR circuit problem onto the computer. So remember, define and translate, we have to break it into pieces, and translate, we have to make the equations ready for evaluation on the computer, or turn them from physics to a problem of mathematics which we can set up on the computer. So we're going to do this. So this is the set of equations we have. First we are going to do is non-dimensionalize this equation by choosing the suitable scales for q, I, and t. We already know how to reduce them to first order ODEs, but first we are going to do is non-dimensionalize them. Without non-dimensionalization, we cannot turn them into a problem on computer, because computers only know numbers, they don't understand physical dimensions. Then we are going to check how many free parameters are left in the equation after non-dimensionalization, that is, how many free quantities are there on which our solution can depend. Then we are going to write the non-dimensionalized set of equations as first order ODEs. We just did this set of equations as first order ODEs. Now once we have non-dimensionalized, we'll take the non-dimensionalized equations and solve and write them as first order ODEs, because those are the ones we're going to put on the computer. And finally, you know the analytical solution. This is the analytical solution. We are going to take this analytical solution and also non-dimensionalize this one, because that's what we are going to go compare on the computer. So let's go ahead and get started with that. So non-dimensionalization, always the easiest way of doing that is find out the scales in the problem for various physical quantities. In this case, physical quantities are q, I and t. So for q, the natural scale present is q naught. For t, there are two choices of scales. Either I can take square root LC as unit of time, or I can take L by R as unit of time. So I will make a choice here. Any of these choices are fine. You can go ahead and try the other choice, but for the sake of this example, I'll take L by R as the choice. And now I need a scale for current. I'll take current is Q naught by T. I've already chosen scale for Q naught and scale for T. So therefore, natural choice for scale for current becomes Q naught R by L. So let me go ahead and substitute this in this set of equations. And when I do that, rather than introducing new variables which are dimensionless, it's always easy to make the following replacement. Replace q by q naught q, where this q was dimensionful q, and after replacement this q becomes dimensionless q, and q naught contains all the dimensions. Same thing for time. The time here is dimensionless time. L by R contains the dimensions of time. This I is dimensionless I, and q naught R by L contains the dimensions of current. So this q, t and I are before the replacement, that is in this equation they are dimensionful quantities. Q, t and I on the right hand side of the arrows are dimensionless q, t and I. So I'm going to go substitute q, t and I with the right hand side values in this equation. When I do that, I get this. Over here I have pulled out dimensions of q and t, and as a consequence I'm getting this factor out here. Again, in my differential equation I got q by LC. So for q I'm writing q naught over q, q naught times q, and that pulls me a dimension of q naught out. Again, pulling out dimensions in dq by dt, dimensions of q out of this and dimensions of dt out of this, I get a factor of q naught L by R. R by L is a constant, LC is a constant, we'll leave them as it is. And now if you simplify, you'll get this equation where most of the dimensionful quantities will cancel out, and I'm only gonna get one ratio L by R square C. This q is dimensionless, this t is dimensionless, so d square q by dt square is dimensionless. This dq by dt is dimensionless because both q and t are dimensionless. This q is dimensionless, therefore L by R square C is also dimensionless, and this is a dimensionless ratio. This is the only parameter in my problem that is left after the translation. So we are done define and translate these two steps. After translate, this is my math problem. It's not completely ready for implementation for Euler's method, but I have to, as far as the math problem is concerned, I have to solve this math problem for a single parameter L by R square C. So every time L by R square C changes, the solution changes, math solution changes. Taking that math solution to a physics solution is all, after that only means I am setting the scale for physical quantities such as q, t and I, which is determined by q naught, L by R, etc. But as far as the problem is concerned, the solution only depends on the ratio L by R square C, or the nature of the solution only depends on the ratio L by R square C. Very good. Now we are going to play the same thing. We are going to reduce this equation to a first order ODE, a set of first order ODE. So we will define dq by dt, the dimensionless charge divided by rate of dimensional charge divided with dt, the derivative of dimensionless charge with respect to time as dimensionless current, and di by dt as minus L by R square C q minus I, where this dq by dt was replaced by I, and the initial conditions q naught of 0 is 1. Again, q is dimensionless, so q naught of 0 is 1 and I naught of 0 is 0. So now this is the math problem that is ready for me to be put on a computer. This is a set of first order ODEs without any dimensions, and the only parameter is L by R square C. Now if I look at the solution, the analytical solution that was given to me for this, which we worked out a couple of lectures ago, I again non-dimensionalize this. When I non-dimensionalize this, my solution reduces down to this equation, where this is dimensionless charge. This is simply an exponential of minus t by 2 and a cosine function of this argument, where I have got the constant square root of L by R square C minus 1 by 4, this constant multiplying dimensionless time, and this constant inside the square root is also dimensionless. Now my solution only depends on the ratio L by R square C. As I saw it in the differential equation, the differential equation only depended on the ratio L by R square C. So does the solution only depend on that, and I can see that this solution is only valid as long as L by R square C is greater than 1 by 4. So that's our domain of validity of this solution, and this is the domain in which will work, and we'll take this parameter L by R square C as something, we can call it alpha, and as long as alpha is greater than 1 by 4, we are gonna have this solution as a valid solution. All right, let's go ahead and work on how to implement on the computer. So before we solve that problem, let's understand the general framework of putting this on a computer. So now in general, I have got a set of coupled ODEs, and in general those set of coupled ODEs can look like this. Let's take work in 3 dimensions. X dot is some function of f, t, x, y and z, y dot is some function of g, t, x, y and z, z dot is some function of t, x, y and z. Now we can express these equations better in form of matrix equations by doing the following. We can define big X as a column vector of t, x, y and z, and big F as the set of functions f, g and h, and I've also appended or prepended this with 1. So f is 1, f, g and h. Now you see that my differential equation, that is this set of equations over here, this set of coupled first order ODEs simply can be written as a single matrix equation, and this kind of setting up will work out really easily on a system like Mathematica, which can directly work with matrices, and a lot of operations on matrices can easily be done. That's why we are setting this up in form of a matrix equation. Now you see that the first equation in x dot equal to f, x dot equal to f is a matrix equation, so it's a set of 4 equations because x has 4 dimensions, t, x, y and z. The first equation is kind of a trivial one, which is dt over dt is 1. So the first equation is saying that time derivative of time with respect to time is simply 1. So that's the trivial equation, and x dot equal to f, y dot equal to g and z dot equal to h is the set of these 3 equations. Now the initial condition also can be written in terms of x0, that is at t equal to t0 I've got x equal to x naught, y naught and z naught. So x naught, big X naught becomes my initial condition, where big X naught is t naught, x naught, y naught and z naught, set of 4 quantities at time t equal to 0. So we are simply going to write x naught as x initial, which is the initial value of time x, y and z, the combination of all 4 of them, and Euler's method simply becomes evaluating xn plus 1 as xn plus h time f evaluated at xn. So this is a matrix equation again. Xn plus 1 is a 4 tuple, xn is a 4 tuple, h is a scalar number, the step size, and f of xn is a 4 tuple because f is a function which is a column vector of 4 functions, where first one is the identity function. So f evaluated at xn is going to give me a vector or a 4 tuple or a column vector of 4 items. So this is how I can go ahead and implement that. Now you can see that the Euler's method code is pretty much going to be the same. I'm going to make minor modifications. The only minor modification I have to make is take care of doing this for all the functions at the same time, that is, do it for the matrix as a single number. So let's go ahead and see how to do that. For that I'm going to use through constructor, through function. What through function does is, notice from this example, when I take some function f, g and h and apply it on x, that is without the through function. Let's do this without the through function, and if I do this, you're simply going to get that back. But when I apply through function on this, as I enclose this whole thing inside the through function, you see I get an array of f applied on x, g applied on x and h applied on x, and that's exactly what I want. I can also implement this through an at the rate operator or prefix application. So fgh is a set of functions that I'm applying on x. When I do use a through, I get f, g and h applied to all 3 of them, and in return I get a list of 3 functions. and if my set of arguments were a vector, as they happen to be in this case, I can apply on the set of vector xy, or for that matter t, xy and z, which is my column vector. I can take it and apply on that. In return, I'm going to get an array of functions f applied to t, x, y, z, g applied to t, x, y, z, and h applied to t, x, y, and z. So we can go ahead and use this through construct. There are two ways of doing this. Either I can use the add operator, or alternately I can also use the add operator in the following sense. If I use a single add operator, I'm going to get f applied to the vector t, x, y, z, g applied to the vector t, x, y, z, and so on. I can use either of these constructs, and it depends on how you define your functions f. So let's work with the add example, and you can modify the Euler general function that I'm going to give you for this example. So let's go ahead and redefine the Euler function for the more general case of multiple dimensions. So in this case, 3 dimensions x, y, and z. Add a time dimension to it, it becomes 4 dimension. So this Euler general is going to be for 3 plus 1 dimension. One is the time dimension, and everything else depends on time. So 3 other dimensions. So again, for this Euler general function, I've got arguments, the set of functions f, g, h, etc. The initial point x naught. Now this x naught is going to contain also the initial point time t naught. So this contains t naught, x naught, y naught, and z naught, all the 4 items in it, and the final time tf up to which I want to evolve, and nmax. Nmax is the number of steps that I want to keep. So you see there's some modification over here. T naught has been absorbed into x naught as part of the initial condition x naught. This is a set of functions, not a single function, and I'll show you how we are going to implement that. Again, I've got a bunch of local variables in the module construct. In order to make things a little bit more readable, I have defined previous, next, and rate. So let's go ahead and understand this code. The first thing I'm going to do is I'm going to calculate h. H is t naught minus ti. Ti is the first element of x naught. So that has been resolved over here. This is the first element of x naught. So tf minus ti divided by nmax gives me h. Then I want to start my for loop, and this is the part of my for loop. In the for loop, again I've got the initialization, the condition, the increment, and the body. So the last 3 statements over here constitute the body, and in the increment I am appending to the data list the next element. The next element is calculated in the body. So let's go ahead and understand that, how we are doing this. So first, in the initialization, x naught is the set of 4 items, t naught, x naught, y naught, and z naught. We are adding all of that into a column vector x naught, and that x naught has been added to data list. This is initialization of data list. Of course, the condition is same as before. Length of data list is less than nmax. And increment, first we're going to execute the body. In the body, we're going to calculate the next, and in the increment part of the for loop, we're going to append that next value to data list. In order to calculate next, I need to first read previous. Previous is read from the data list. So I take previous from the last element of data list. In the first run of the for loop, that will be simply x naught, because data list only contains one element x naught. Then I calculate the rate. Rate is given by application of the function on the previous. So each function, that means, should be of the form, it should have 4 arguments. Each function should be of the form, it can take 4 arguments t, x, y, and z, or whatever the number of variables we have. The way this code is written, it doesn't care about how many variables you have got. As long as the size of x naught and the function is same, this will be fine, because size of previous is same as the size of x naught, and function requires the number of arguments the function requires should be the size of x naught or the size of previous. So this is going to pass each of the functions, the arguments through is going to make sure that each of the functions in my array are passed on the arguments in the previous, and the rate is calculated. So that means I calculate capital X dot from here or big X dot from here, and next is calculated by adding previous times h plus h times the rate, or h times the X dot. So this is the instantaneous X dot at the previous point multiplied by h, that gives me the step size. Adding that to previous gives me the value of the next step. I execute this for loop. When the for loop ends, I return the data list. Let's go ahead and run this function. Now that this definition has been made, let's go ahead and implement this for the problem that we are looking for. The problem we were looking for is this set of equation for the LCR circuit, the damped LCR circuit. Damping is because of the resistor and oscillation is because of LC. So my equation is dq by dt is I, di by dt is minus L by R square C Q minus I, Q naught is 1 and I0 is 0. It's better to actually write this equation as, so this is my Q dot. So this is a function of only I, and this side I dot is a function of Q and I. These are the only two variables. So you can think of Q as X and I as Y. So this is dx by dt and this is dy by dt. And we have got X of 0 and Y of 0. So therefore, in order to implement this, what I'm really doing is I am writing my big X equal to Q as a two tuple of Q and I, and of course I have to include time also. So I can go ahead and include that. So T, Q and I is my X, and I'm writing X dot as, again, this is 1, this is simply I because Q dot is I and I dot is this. So this is my differential equation written in the matrix form. This is my differential equation in the matrix form. I want to solve this differential equation, and in order to do that, I'm going to take this ratio L by R square C as W. So this is what I've defined as W, and for just for reference, I've also defined beta because beta is square root of W minus 1 by 4. This is the part that goes into the analytical solution. So I'm going to take W as 10, which is much bigger than 1 by 4. So to start with, this is 2 pi by beta. Beta is the oscillation frequency in my analytical solution. So 2 pi by beta will give me the time period. Now I want to define these three functions. This is my first function, this is my Q dot, and this is my I dot. The third argument over here is I dot. So in order to define that, I'm going to call the first one as identity, this one as identity. So this is defined over here. This is identity, and this is simply 1, but it has to have 3 arguments because my code wants each of these functions to have 3 arguments. So this one is a trivial one. You have to define an identity always in order to run the code. It should have 3 arguments: time, charge and current, and independent of those arguments always going to return 1 because dt by dt is always 1. Then charge dot is Q dot. It is again an argument of t, charge and current, but it is only a function of current. So therefore Q dot is only equal to current. And then finally current dot, which is the principal part of the differential equation, again is a function of t, charge and current in general, but in this case it is minus L square by C, which is W times Q minus the current. So therefore current dot is the third equation in this matrix equation. And finally the initial conditions are to set. The initial conditions are at t equal to 0, I've got Q equal to 1 and I equal to 0. So this is my set of initial conditions. When I execute that, I suppress all the outputs using the semicolon over here. So when I suppress, the only output that I'm printing over here is this. So when I take W equal to 10, beta is square root of W minus 1 by 4 and 2 pi by beta is 2.01. So this is my time period in the dimensionless units of time. Now I'm going to go ahead and evaluate this. Notice that for the Euler general function, I'm going to pass the first argument. First argument was supposed to be the set of functions which are defining x dot, and those set of functions are id, charge dot, and current dot. So this is a set of three functions. id is just one, this is q dot, and this is I dot. Initial condition, again the size of initial condition is 3, and size of the function has to be also 3. If these two are not equal, you run into some sort of error. Then final time is tf is 10, and number of steps I'm going to take as, let's say, 100 to start out small. Let's go ahead and actually go ahead and execute this. 100 I can print on screen and read, so let me remove the semicolon. I'm going to execute this, and there we go. This gives me the expected result. I see an array of set of 3 points. This is my initial condition, this was the initial value, and then some changes happen to the initial value, and then some more changes and some more evolution, and so on. We get evolution up to tf equal to 10. So this is the value of final charge, and this is the value of final current. Second value is always the charge, and third one is the current. So let's go ahead and plot this. In order to plot this, here is my comparison. What I have done over here is that I'm doing a list plot of the data that I've just calculated, and in the data I'm taking all the rows but only the first and the second column. That is, I'm taking the first column is time, the second column is current, charge. So I can go ahead and actually, in order to make it more readable, I can do this as table form so that you can see. So the first column is time, second column is charge, and the third column is current, and I want to take all the rows. This is for all the rows but only the first and the second column. So that gives me q as a function of time, or q versus time data, and I make a list plot of that. So that gives me, this part gives me the list plot of that. And so let me put the plot markers back so I can see, and then I'm comparing this with the analytical solution, which is in the red. Analytical solution is e to the minus t by 2, the non-dimensional version of the analytical solution, cos beta times t beta was square root of w minus 1 by 4. W was a dimensionless ratio of LR and C. So this is the analytical solution. I want to compare the analytical solution with the solution that I've got, and I see that this comparison is really bad. I think I have put a table form here, so let me remove this table form because I want to take data as a list. Let me put a semicolon back again now that you understand. So let me put back the semicolon here. Now I'm going to do this comparison, and there we go. So this is my analytical solution, and it doesn't really work very well. It doesn't give me any comparison, any good comparison with the analytical solution. So let me go ahead and see if this is because of h being large. Let me make it number of steps is 1000, so h becomes small, and compare that. That's a significant improvement. In order to see that, we tried as 100. Let's try 500. It is in between. So 100 was really poor. In order to just verify that, this was 100. 100 was extremely poor. That means errors were large. 500 is getting better, and 1000 is even better. This is 1000, and finally 10,000. If I go ahead and do the 10,000, you'll see it's a fantastic agreement. Actually, not that great, but we can actually go ahead and increase it to 20,000, and you see from 10,000 to 20,000 is a slight amount of improvement, if you notice that, but not a significant amount of improvement. Red and black curves are not exactly on top of each other, but very close to each other. It's quite decent. So you can go ahead and play with values of beta So in order to play with value of beta, what we need to do is or L by R square C, that is W. I can go ahead and make W even smaller. If I make W smaller, the oscillation frequency becomes larger, time period becomes 2.88. We can actually compare the time period. Also, before the time period was 2, and that is about right. From peak to peak, the time period was 2, and now it should be close to 3. So let's go ahead and check that. There we go. Here's our comparison. We changed the value of beta, so the curves changed, or we changed the value of W, so the curves changed, and our time period from this peak to this peak is about 2.88, which is slightly less than 3, which we can see from the plot over here. It's a good idea to actually check some of the basics while we're doing the computation, so that we know that computer is doing what we intended to do. We have not made some sort of mistake. When W is 20, L by R square C is 20, so therefore this is going to, the R is going to be very, very small, and as a consequence resistance small. That means I should have lots of oscillation, and you see the time period reduces down to 1.41. Let's go ahead and do this for 10,000 points, which should be enough. The execution is done, so let's go ahead and compare, and we see the comparison is very well. Let's try to re-obtain the limit when the resistance is very small. Let's make this even larger. Let's make W equal to 100. That is the case when resistance becomes small, and we can go ahead and evaluate this and do a comparison. Now you see, as I make W larger and larger, the damping becomes much more slower, and there are more oscillations that are happening. That means by the time amplitude decays to 1/3, we are going to cover more oscillations. We can go ahead and check that back. When W was 10, for W equal to 10, we can see that amplitude was 1 over here. By the time it dropped down to 1/3, which is about here, we have covered about just about 1 oscillation. And as I increase W, make it larger, let's say make it 100, and there we go. By the time the amplitude drops to 1/3, that is about here, we have covered about 3 or 4 oscillations. So that means we're going more and more closer. The damping becomes less and less important, and we're going more and more closer to the regime where we're going to just see the oscillations and not much of damping. And you see that at these turning points, the agreement is not very well, and that is because of the limitation of the Euler method. We can try to improve it by making this, increasing the H, and let's see if that gives me any significant improvement. It does give me a little bit of improvement, but see, to get that much of improvement, which was about, fraction of a maybe just about 4 or 5% improvement in this region over here, I had to double the number of points. So the computational cost is very high with the Euler method. At least that is what we noticed from this exercise, that the computational cost with working with the Euler method is very high, because local accuracy is order h square and global accuracy is order h. So I have to keep on, in order to improve the global accuracy of my solution, I have to linearly scale down h. That is, I have to, in order to improve the accuracy from 0.1 to 0.01, that is by an order of magnitude, I have to take 10 times more points. So in order to improve accuracy by 1 order of magnitude, I have to take points 10 times more, which is a huge computational cost. This is something we can improve by using better methods, such as the improved Eulers method of the second order Runge-Kutta, or even better, fourth order Runge-Kutta, which is an accuracy of local accuracy of h to the power 6 and global accuracy of h to the power 5. Before we do that, let's go ahead and quickly check. We did the plot of current versus time. Let's go ahead and do a plot of current versus time versus current. This is time versus charge. So in order to do time versus current, you need to extract the first element and third element of the data. So this is all the rows of the data, but the first and the third element, first being the time and third being the current. So if I do this and compare this with the current, you can work out the current equation for the current. I is a function of t from the analytical solution. You'll find that this is the solution, and you can do this comparison, and you'll see this is also in fair agreement.